Okay, nice short section, guys. This is stuff that you have been using in maths. I just want to show you where it comes from. We've been through it in the lesson, so this is just a case of filling in your notes effectively as we go through. So, crucial thing is, this is anything to do with a straight line velocity graph. Okay, it will not work. You cannot use it for anything where the velocity is changing. So, for example, imagine a swing. Okay, the velocity is not constant, it's changing all the time. So it's changing here all the time, but this changes in a constant way. If you're on a swing, as you gain up, you've actually got more force slowing you down. The forces change. So here we have a steady constant force. That's why that is the correct way of thinking about it. Okay, if it's not uniform, if it's not a straight line graph, it's not going to be a suvat question. Okay, so suvat are your simple way of remembering it with the correct units. All of them have to be SI, so they have to be System International units, etc. Okay, nice and straightforward. They're all based around this graph and different ways to find out useful things from the graph. So acceleration is rate of change of velocity. Okay, so how do we get that? So gradient, yeah, because that's our change in velocity over change in time, so rate of change of velocity, which for a straight line graph is also the average change in velocity, so it doesn't make any difference. In terms of our letters, we will reach a second speed, our final velocity v. We would go from u to make that happen, so I'll just make that across because it's there. Obviously it will be read off the axis, but your gradient is straight and it's going up and it's taking a certain time. So, simply, how much has it gone up? Change in velocity is v minus u, okay, and the time it's taken is literally time t, because this is 0 over here on our graph. If it is partway through a graph, then whatever the length of that time is there, okay, so I'm going to make it obvious. That's t minus u, and that's t minus 0, and that's v minus u. Okay, so that's how we get it. So nice and straightforward. Rearrange that. That's going to equal, as I say, acceleration. The form that most people tend to use and is on the data sheet is your initial speed, start, so this kind of idea here, plus the changing part. So that's our equation on the data sheet. Okay, so nice and straightforward. Very, very simple. One from GCSE, I should say, and one from the actual definition. So really nice and simple, brings it all together. Displacement slightly more awkward. Okay, so this is how do we link it to this idea of average. So actually, if we assume this, the simple way of doing it is, okay, my average of those two is add them up and divide by 2. Okay, so it's really straightforward. All we're actually doing is S equals better put in average, times by t. Okay, so nice and simple, because you got that nice simple thing is the average equals u plus v, okay, two values, and divided by 2, times by half. Okay, so if you put those in, then all we've got is very simply that idea of, and make it nice and simple, v average equals u plus v over 2. Okay, please notice my v's have the little tick at the top. Therefore, if we put that in, excuse me, s equals u plus v over 2 multiplied by t. Okay, and the format that you tend to see it in the equation is written as s equals half u plus v t. It's the equation that most people forget, but it actually is really useful. Okay, really, really useful. Now, the next one is if we break it up, and I tend to use this, and this is the reason most people forget. It's worth putting in that this is basically the same as, which is what I did in the lesson, same as parallelogram rule. Okay, so how we use a parallelogram to add up area. Okay, but think of it far more usefully as this. Okay, the average of the velocities halfway up the graph, halfway up the line. Okay, the next one is where it starts to get a little bit more complicated. And there's two ways of doing this, but one of them tends to be used, only one of them is in the exam book, and it's the one that tends to be used by most people. I don't just mean for physics. So what we're going to do here is simply add up that area plus that area. So we'll treat it in two different bits. So we're going to take S basically equals area A plus B. Okay, so excuse me. What we've got for A is simply that multiplied by that. Okay, so that's going to equal UT plus, and then we've got this. So again, T minus 0, so T, size by that. So if we multiply those together, we'll end up with that rectangle at the top, and we just divide by 2. So half of V minus U, okay, multiplied by T. Now that's a little bit messy, but we can use our useful equation up at the top. So equation 1, you'll notice I've written equation 1 in the box above the box. So if we use equation 1, then what we can do is simply get rid of some of the stuff. So V minus U equals AT. So rearrange that ever so slightly. Okay, and I've got V minus U there. So what I've got is then S equals UT plus half AT multiplied by T. Okay, and that simplifies to the bit that actually is really, really useful. S equals UT plus half AT squared. Okay, and that's really, really commonly used equation. So that's great. That's great. That's often forgotten about, but it is useful. Okay, it is another way of doing it. We should say that actually we can subtract that area, which is the same as B. We can subtract it from the maximum. Okay, so if we really wanted to, we could actually do it another way. Alternatively, what we could do, as I've done down here, is ignore the graph and just take that value and subtract it into this value. Okay, so what we can end up with is alternative proof, let's put it that way. U plus AT, okay, so that's number 1, and that's going to go into getting rid of the V in this version here. So S equals half, let's take the half out, U plus V minus, sorry, what was I saying? Get rid of the V in there, so that's going to be another U. Plus, that's really mucky, excuse me, plus AT, okay, multiplied by T, which simplifies out as you got U plus U, so that's 2U divided by 1, multiplied by T, so that's still going to equal S equals UT, plus, and you've got half of AT squared. There's always more than one way of doing it. So that's just playing with our previous equations, but both of them are based on that graph. So it's actually just the same as using the graph, just a different way of doing it. Okay, and then last but not least from this chunk is how do we get the other equation. So this is really important because of what we don't have. So you don't always have the time. Okay, I mean, not in an exam, but you don't always have the value of time it's taken to accelerate. Okay, so as it says here, then we need an equation without, scrub that, without t. There's a mistake I haven't noticed. So what we can do is again take the first two equations, but this time use it to get rid of t. So what we'll have is S equals half U plus V, okay, times by T. I told you it was a useful equation. So you've got that, but we need to get rid of T. So what we can do is from V equals U plus AT, I need the T. So what I'm going to have is T equals V minus U divided by A. Okay, so what I can do is stick that into here instead of that. So we end up with, I'm going to put these together because it will make it a little bit easier. So I'm going to have, I'll put the 2 under that one. It doesn't matter where I put it, to be honest. But instead of that, we can have v minus u over a. Okay. And what I can do is just take the 2 and the a across, then multiply together, so it doesn't matter. Effectively, that's what we've got, one simple equation. So I've got 2as equals, and then we can do this. So we've got uv, okay, first, outside minus u squared, inside plus v squared, and then last, so minus uv. Oops, excuse me. So obviously that cancels with that, we just end up with that. So we end up with a nice convenient form that runs really nicely, and we tend to write it with a v squared on its own. So I can add that onto this side. So v squared equals u squared plus 2as, which at GCSE you tended to have as v squared minus u squared equals 2as. Doesn't matter. Okay, it's just rearranged. So all of those are crucial. All of those have a steady part, so the initial speed, what it all depended upon, and they all have some sort of acceleration phase. Okay, something with acceleration in. So that's our changing part, that's our steady bit to start with. With all of them, if they've got a u in, and whatever it has started at rest, then that simplifies. So this would be v squared equals 2as. And you can happily put that as 0, or put an arrow through and put a 0 next to it. Okay? Now, the crucial bit is, if we just go back into all our equations, just take that out, this equation has no t, so you can work out the missing letter that you need without having to know t. For this one, there's no s in it, so if the distance travelled during the acceleration is unknown, then that doesn't matter. You can use that equation. Okay, in fact you have to use that equation because it's the only one without an s. This one here, well, we've got the u, the v, the s and the t. We don't have a, so if the acceleration is unknown, okay, so we'll go down to the next one. We have no v, so v is unknown. I should say you could have vt minus half at squared, in which case that's if you don't know u, but you don't need it. All the questions you can find it a different way. So if we run through those 4, we have s, u doesn't tend to come up, v, a, t. So all of them are missing from one of the equations, all of those. So if you lay them out right at the beginning of your question, S, U, V, A, T, in a nice simple line, and then you can tick them off. So literally, yes, I've got that. That equals 20 meters, whatever. U equals 0. V equals, I don't know, I want to find that. A equals unknown. T equals, 17 or something. You can then from that go, well, I don't know a, so I need the equation without an a. It's going to be this one. So you've chosen your equation by using out your layout. Okay, so do that every stage and then just think which of my 4 letters are missing from the data book. And again, don't forget the data book is really, really powerful. You may want to go in at this point. Let's try and open it. There we go. And they are there right at the beginning of section 3, and that again is, there's no S, there's no A, there's no V, there's no T. Okay, so that's kind of crucial. That's how you go around choosing the right equation. Okay, that's brilliant. Thank you very much.